VirtualBox, do you?
Yeah, you do need the VirtualBox too. But there's some codes there I want to show you.
So who has downloaded the thing? Yay. Right now it's for sure on 2014. If you go to 2014 and you scroll down to July 14th, you see Seismo tutorial 2 and there should be a zip file right there. Jeroen. Now it's also on 16. Thank you, Dan. Is anyone horribly confused? So there are going to be two aspects of the tutorial. One is done in MATLAB, and that's the one that we used 2 years ago. The other one is Jeroen is going to talk to you about, and that one uses a virtual machine. So on the virtual machine, what's the name of the folder with that one?
It's called, sorry. It's something called like CIDER tomography plotting, something like that. I'm not entirely sure.
CIDER user. Yeah. Well, for the first half you won't, but then for the for the actual inversions you will. Who has MATLAB? Wow. Okay, so if you don't have MATLAB but would like to do a tutorial, find a buddy who has MATLAB. Seismology is always more fun in pairs.
Do you have everything? Okay. So everybody has everything? Is everybody ready? Not really? Okay. You guys ready? You got it all? Not yet? So I want to show you basically two things. The second portion is is a tutorial that I got from VET and from Mark Penning, who wrote that 2 years ago during the previous or showed it during the previous CIDER workshop. But I first want to show you a script that I wrote that may be helpful, in the next couple of weeks when you're looking at tomographic models, if that's going to happen, especially, if you're going to look at tomographic models. So I wrote a script that basically takes 5 models, or 6, I can't remember, which you can use to simply slice through it. So you can take cross-sections or maps, you can make cross-sections or maps of these models, and you can compare them. So they're all uniform, use the same color scale, so you can directly compare all 5. And so that's in the virtual box, and there's 2 codes there. The 2 codes there. One is called MKCR underscore all, and make map mkmap underscore all. And those are the 2 scripts, the C shell scripts that you can run to on the command line to make a PDF, to make a PostScript. Sorry, a PDF file, and then you can plot the PDF file with preview or echo read or whatever you use. Okay, so I'm just going to run these, and then you'll see how it works. And so it shouldn't take too much time, but you can basically play with it. Excuse me? Yeah, it's on the desktop, and the folder should be called tomo underscore plotting underscore CIDER. Is the folder empty? I'm not sure what's your. What's your problem, Ida? Open a terminal and then CD into the folder. So let me just run the script, and you get the idea of what you can do with it.
So you just run it by typing the.
So yeah, just type in what I type in. So the command the way you run it, you should type in the script name mkcr underscore all, and then you if you do the / I always do that because that makes it that explicitly say you're running it in a current directory. Okay. Yeah, you need the / that's better. Yeah. And then you give it a location. So let me just type one in. I put in Hawaii. Right there. So what I type in here is essentially the location of the slice that you're going to draw. So that's the location of the midpoint of the slice. You'll see that in a minute. So this will be Hawaii, 20 degrees north, 150 degrees west. And then the 30 is the azimuth in which you are directing the slice. Okay. And so these are the 3 variables that you can play with. So latitude, longitude, and an azimuth. And there is a README file in the directory that should explain all these things. So when you hit return, it will basically, oh crap.
It works on the virtual machine though. I don't know why.
It's in my local, crap.
The virtual machine, you have to be careful. There's one working GMT and one is messed up. Our friend in the CIG
Does anyone need my personal assistant? Oh.
No, I was not running it in the right shell. So it's going to run 5 programs. It's going to run the same thing 5 times for 5 different models. Yeah. can't hear you. Better? So if you run that routine, you should have gotten a PDF file, which is called slice.pdf. Okay, if you get JPEG, then use JPEG. If you can open a JPEG. Okay, I get PDF, but that's what's that?
Can we get the scripts?
Can we get them from the virtual box?
How can we download them to our iPhone?
They're in there. They should be in the.
The virtual box. I don't know how to get them. That's nice. You told me to get them.
Yeah, you get them later. Sure.
Oh,
Yeah,
we
yeah.
do get them.
Yeah, yeah, sure.
So what's the problem? You know how to virtual?
We're doing it together.
Oh, got it, got it.
Did it work? Okay.
So who has produced this pod?
Okay. So and that's what I wanted to show you. So you can actually you can make slices. You can slice through these different models, and then you can talk about them.
Yeah.
So maybe we can look at these a little bit and see what the differences might be. If you learn something from Vet's talk, maybe you can see why things might be different. It's actually a really difficult question I'm asking you to address, but let's, for example, look at the last model. It looks very empty in the lower mantle. Why would that be? It's a highly damped model. It's also a model with very few data in the lower mantle. So if you have no data, you don't get a model, right? Anyway, these are fairly typical differences between global scale models that you get. So, and the differences are for all many different reasons. Mostly, I would say mostly data coverage, but other damping, regularization, all the things that Ved talked about, all the types of choices that you make to produce a model, it's all going to matter how the images will look like. Right? Yeah.
So are they all, for the most part, using the same data?
No. The last model in particular, the last model is actually a Pwave model, and it's only based on direct and surface. Sorry, I think it's only direct P waves.
I think they have some PP.
They might have some multi-bounce P waves, but not many. So this is mostly P model, and it's only travel times. The other models are very similar in nature. The gypsum model is predominantly travel times. I think only travel times. Is that correct, Steve? That's only travel times. The other models are a combination of travel times, dispersion, mode frequencies, mode splitting observations, things like that. Right? So you see differences. You see, for example, look at the LLSVPs. You could see sort of differences in their detailed shape, maybe the extent that they rise into the mantle. Some of them have, maybe on the edge, a plume-like structure, like this SEM model has it very clearly. Others don't have it at all. But these are very typical differences. Yes?
Can you comment some more on the choices as to radial versus horizontal damping in the top model?
In the top model, there is no vertical what do you call it? Vertical smearing or vertical regularization.
Explicit. There's a lot of implicit virtual.
I mean, compared to the others, I wonder.
I don't know what's
These
two.
one, and this one are probably fairly similar in
Yeah.
terms of their vertical smoothing. This one I think is uncorrelated, but Steve can.
I think that has a little bit of vertical smoothing, but the horizontal is much stronger.
And then this one I have no idea.
Yeah. The gap, again, the gap 4 model, I put it in there. I had it. I just had it. But it's a P model. But it's a very nice illustration of what happens if you have no data. You get no model, right? I mean, that's no surprise.
Which P model is that?
It's Obayashi and yeah, the most recent model from Fukao, Obayashi, and Nolet, I think, is his third author. Yeah. We can do another slice. I mean, if you kind of like this.
Yeah. Does anyone have a desired location?
Yeah, location azimuth.
Nigeria. No, it's probably a good place to try. West Africa is one of the least well resolved.
So what is the African plume? All right. Oh, sorry. I already did my.
He did South
I
Africa.
did my favorite slice. So here's your Eastern African slice. See also the differences in amplitude. Some models are much weaker than others. So the top model is a highly damped model. It's implicitly or explicitly looking for the smallest perturbation from the standard model that you can do. So you get therefore weaker models typically. That's a good question. I actually you might actually have a slightly different model for this because I actually multiply this by a factor of 2 because the P-wave variations are typically about twice as weak as the S-wave variation. So I multiply this by a factor of 2 to correct for that. Yeah, well, why do you think that is, Thorsten? Oh, sorry, I got off the screen. I think it's data coverage. I think this is a particular slice that's reasonably well covered from this, from the. So you get similar data. You get similar data goes into the models. You get a similar model. I think if all the data set, all the models derive from the same data types, then you will get the same structure. And then many of the differences here is regularization, is damping, for example. So the top model is more damped than the other models.
So are you saying the data selection is more important than the assumptions about mutation?
I think data wins. Isn't that what you said during lunch? Data always wins. Is that what I thought you said that? Yeah. But again, this is the character, right? I mean, we can talk about things. Are plumes split in half? Are plumes, or if these things are super plumes or whatever you call these things, are these sort of breaks in the structure? Are they real? This is the typical variations among models that you'll see in the mantle. So you really have to go down into the nitty-gritty of the inversions and of the choices that you make in order to assess that. But we all agree there is something really big under Africa that's sticking up. Right? We all agree on that. In fact, you can see that in the data. There's no surprise here. Okay? Yeah.
It's on.
Just a naive question. Do these all start with a 1D, like Prem-like velocity structure? And is that why there's kind of I see there's a dashed line at 660. So
Dash line is 660. Yeah, that's just a marker. That's just
okay.
to orient yourself.
So they don't have like a predisposition towards like stratification, discontinuity at 660.
Well, some models do have. I'm not sure. This model, I think, has a split parameterization. Is that right? Yeah. So this model, you might actually, the model itself is parameterized differently than the other models, where you actually have explicitly a break in the parameterization at 660. Okay. So that might be, that sort of, the strong contrast that you see between above and through 660 might be an implicit regularization as. vet would call it. But yeah,
Thanks.
yeah. Most models start off with a 1D model, but these variations upon the 1D models, the scale bar is about a couple percent, 2% or so, 1.5%, up to 2%. So the variations upon these reference models is typically on the order of a couple percent. So the starting model is not too critical. Okay.
Can you plot one up through Nigeria?
Nigeria. You have to tell me where Nigeria is.
So if you go, I guess if we did like 0, 0, and then made the angle 90, it would go north-south. Is that right?
East-west.
So 0 then. 0, 0, 0.
Oh, you want north-south?
Yeah.
You can spend a lot of time doing this. So it's a dangerous thing to begin a...
We should have ended with this.
Yeah.
What format are the input files in? If you wanted to add a different model, for example.
Yeah, so I took the models that I had a week time to do this, so I took the models that I already had. I put them in a parameterization I'm most familiar with. But if you send me a box with lat longs and values, I can do that. That's not a problem. Yeah. You have a model in mind? Yeah. Yeah. No, it would be if I have a box of lat longs and depths and values, I can just put it all together. It's no problem.
Harmonics, is that what
These are all
SPH is?
parameterized in spherical harmonics, but that's just the way I parameterize things. But so this is a very interesting slice actually, because here you might actually see an artifact of the 660 parameterization. You see here a plume, or you see here something red sticking up in the mantle, and then sheared off by the 660. Okay, I would argue that it's probably not a real feature. It's probably something related to the parameterization. Well. Yeah, well, I mean. Yeah, this is this stuff here. You mean? Yeah. Yeah. Of course, you realize also that the scale used here it's a uniform color scale. So you're highly saturated in the upper mantle. So the variations between red and blue is more than 7% in the top 100 kilometers, where the plates are, and it's maybe only 1 or 2% in the transition zone. So you might see a continuous blue blob going from the surface to the 660, but by far the strongest variations are in the top of the mantle. You can modify the scale factor or the tomographic scale. That's in the script, but that.
And if you guys want to look at other tomographic models, Jessica nicely pointed out that IRIS has an Earth model repository where you can look them up. I think it's like EMD, like IRIS EMD. If you Google that, you'll find it.
Okay, shall we go to the tutorial?
Yes. For this part, you will need to use MATLAB.
Yeah.
Oh, and in the MATLAB directory, there's a single .m file called inverse tutorial. That's the only one you need. All the other ones are kind of helpers. Like, you only need inverse tutorial. That file contains everything. Who has located inverse tutorial.m? Okay, cool. Yay.
So the problem that Ved and Mark Panning put together is basically the problem that Ved talked about very late in this talk, where you had basically a grid, sort of a 2D grid of blocks, along which you had rays or earthquakes and receivers sampled by rays from sampled by rays. So it's a two-dimensional problem. Okay, the problem is not a travel time. Well, the problem is a travel time model, and it's basically written out here in this equation. And so essentially, it is you're looking for variations in wave speed. In this case, you're looking at variations in surface wave speed across a surface. Okay, so the tomographic model itself, or the tomographic problem, is cast here. You're just looking for, you're actually measuring delays or advances of the wavefront from a source to receiver, and you basically write out the observed wave speed variation as an average along that ray path. So that's how you cast the forward problem. It's a very simple way of casting it, and it's cast here as a line integral. So it assumes that the waves essentially propagate along a line. So it's a ray theoretical formulation. Okay, so if you go down that, then you discretize the problem. So here you're making your first choice. Here you're making the choice of how you are parameterizing your Earth. And so you're choosing here a number of blocks, a total of m blocks that are parameterizing the area of through which the waves are propagating. Right, so that's your first regularization right there. Right, so you discretize, and then you can write out essentially here's your data vector on the left. These are the sensitivity. So basically the length of the line segments that the waves go through the blocks. That's the G matrix, and this is the model matrix. That's the matrix M that summarizes all the wave speeds in each individual block. Right. So that's basically what Ved already talked about. Right, so there it is. So there's your problem. D is GM. That's the discretized inverse problem. Data vector is your sensitivity matrix times a model vector M. Oh, thanks. Okay, so let's go to the exercise. So maybe you want to start, because it takes a minute or so to actually load the data into the data vector and the model vector. So you need to run the first block of inverse tutorial, and you have to so try to do that. I'll do that the same thing, and then you have to make a choice of which data you want to load. So
So when you do that, you'll notice in this file that there's a couple of lines that have two percent symbols. Those lines essentially define the beginning and the end of a kind of block of code, and you can run that section of code by typing Control Enter. So as long as you click inside there and then press Control Enter or Apple Enter, you should be able to run that portion of the code. And then it'll ask you a bunch of questions which you have to answer in the command prompt, like what is the block dimension? So we're going to divide up the Earth into little blocks. How big should those blocks be? And then what period you want to look at. And the period of 50 seconds is going to be sensitive to more shallow structure. A period of 150 seconds is going to be more sensitive to deeper structure.
Yeah. So I'm going to run this. So you click on block 1, and you type in Apple return or command return, right? Depending on if you have a PC or Mac. So when you do that, it'll ask you first the size of the block that you want to use. The smaller you do, the more model parameters you're going to have, the bigger your inverse problem is going to be. So I think 5, is that right? That is a good number. 5 is a good number for this. So when you're setting here 5, you're basically telling the inverse problem to look for variations in wave speed in blocks that are 5 degrees by 5 degrees in size. Okay, so roughly 500 by 500 kilometers on a circle Earth, on an Earth surface. And that I don't know how many parameters it will give you, but this will give you plenty of parameters that makes the problem already fairly lengthy. So don't go below 5. Oh, shoot.
If you don't answer a question, it might not work. I think you have to do the control enter.
Okay, I'm sorry, I screwed it up. So you do this. So I do 5. If you do 50 seconds, do type in 050, otherwise it will give you a bug. It'll give you an error. I'm going to use 100. I like 100. It's a nice number. The central period, that's basically the reference wave speed of that particular wave. So I'm going to look at a 100-second Rayleigh wave. The 100-second Rayleigh wave is predicted to propagate with a wave speed of 4 point something.
And those numbers are
What is it about? 4.2? No.
4.28. Those numbers are in the
They're
in the
tutorial.
green comments in the actual MATLAB tutorial.
So for 100 seconds, it's 4.008. So that's the reference wave speed. That's the expected wave speed for a 100-second Rayleigh wave. So that's basically the middle of your tomographic color scale. Yeah. It's Prem or?
I believe it's Prem, but I think for 100 seconds Prem is
100
very
seconds,
good.
It's really,
Yeah.
it's pretty good for most models, yeah. Okay, and then so you do that. And then the third question, just type in 1. That basically is the way you actually are setting the data variance.
So these data come from Jeroen Ekstrom, and he actually provides uncertainty estimates on the phase velocities that are kind of hidden from you. And if you use those, you can use his estimates as they are, which would be like typing 1, or if you type 10, you would make them 10 times bigger. Or if you write 0.1, you would make them 10 times smaller. So you can explore the variations in the damping.
Okay, but now I need your help, because what's this? Block S. Oh, I have to run it. How do you open it? How do you do that again? Hey, you want this thing?
Has anyone gotten it to the point where it's actually like plotting things like it, not like writing things as if it's working?
An additional issue also,
Okay.
which is that it's trying to call a function called Euler, and some versions of MATLAB already have a predefined function called Euler. So
Thank you, MATLAB, for updating. Okay, so in that case, you should do a search. If you find this problem with Euler, the way to fix it is you do a find and replace inside that inverse tutorial for the word Euler, and replace it by like Euler 2 or something, and then change the name of the MATLAB Euler.m file that's in that directory to Euler2.m. That should work. That was not the case in 2014.
No, I think it doesn't know where to find it. I think that's the problem.
Well, where are you running it? You have to be in that folder, in the current. You see it says current folder? Go there, and now try running.
Okay.
So we don't have that problem.
Sorry.
So who has an Euler problem that needs to be solved? Whoa! Okay. Who feels like they're completely lost and don't know how to start solving it? It's okay. You do? Okay, I'll come over there. And then I'll go to you. And in the meantime, help each other. So yeah.
So did you guys get a map? Did everybody get this map or something like it? Okay. So the map basically tells you where you are having data. Where are the waves propagating? Where they're not propagating. So it's a hit count map, and it tells you the density of coverage on the Earth. So you see here a classic problem. Again, a problem that is very typical for tomographic problems is that you have highly variable coverage, highly variable variations in strong variations in hit count across the Earth, right? So most earthquakes occur in the Western Pacific, right? Most seismic stations are in the Northern Hemisphere. So most paths are in the Northern Hemisphere, and most paths go from the Western Pacific either to Europe or North America, right? So you see that streak along the Circum-Pacific. Well, that's if you ever fly from North America to Japan, this is how you fly. You're flying across the rim of the Pacific. And very few data in the Southern Hemisphere because waves just don't go there. Right? That's a log scale, what you see on the right. So it goes the scale goes from something like a couple thousand to a couple of 10 or 100.
The clarification for this is go into sray.m. There's a single line where the word Euler appears. Change it to Euler 2. And then there's a single .m file called Euler that's in that same directory with all the other ones. Change its name to Euler 2. Okay? And that'll solve the problem. But I'll go over there. I blame Mark for calling it Euler. So you want to open S-ray? Yeah. So click on.
We've changed S-ray, renamed the function,
Yeah,
and the file is
yeah, and the other thing is make sure that your MATLAB is in the same directory as this script. Otherwise, it won't know how to find all the subroutines. So if you're getting something like block problem or something like that, that's that. But I see lots of nice plots on people's machine.
Yeah, is this the right path?
Oh, okay.
So you need to go. You need to find the path. I think it's right there, where you are.
Sorry, I have never seen
where
that
you are
before.
actually are where you are running this thing. So you. So you need to be able to. Yeah, you need to be in. Well, you need to be in the. You need to be in the path where.
But I thought I had some weird issue. So great, it's working. So when it's done, it's gonna make this. Yeah. Yeah, Alex.
Let me ask that because
I think it should be fine. I just set the path. Added the path here.
That problem over there probably means that you are using. You don't have the right mapping toolbox.
I had to zoom in, and then
Oh,
when I first,
it's fine.
when I first plotted it, it looks like this. So I tried to zoom in. Yeah,
I'll tell you
there's something there. And
Can I see your MATLAB?
Yeah. And then I see.
That's weird. So, yes, that's what you have to do. If MATLAB gives you an error message that says bitmax is now called flintmax, kill me, right? This is a really easy one. So when MATLAB gives you those, if you click where it says inverse tutorial at 190, mgrid at 263. So if you click on that, replace the word bitmax with flintmax. This is a weird MATLAB thing that MATLAB did. Once you do that, your plot will look beautiful. That won't prevent the plot from forming. It'll just be ugly. Once you do that, the plot will look nice. So if you get a message that says bitmap has now been changed to flintmax, you can click on at 269 or whatever, the orange warning. If you click on it, it's going to take you exactly to the line where that word appears, and you can replace it. Did it work? But it seems like most of you don't have that problem. Anyone else stuck on Euler or running? Yes.
And who has the map? Everybody has the map, or many of you have the map. Okay, let me wait for a couple more minutes.
What's up?
Because if we lose somebody right now,
You're not in the right directory.
you'll never get back.
So here, just go up here.
That's my experience.
You're not running it in the... No, you went to run it. Click X. The left of there?
Yeah.
Is that thing? Oh, it doesn't work. Okay. This is in desktop, so click on Pilar.
You mean the type of data or the who made the data?
And then click on desktop.
So these data are Rayleigh waves.
16.
So they're waves that are rippling on the Earth's surface. It's like a wave. If you throw a stone in the water, you get this rippling on the water surface. That's exactly the same type of wave. So the surface waves, they propagate horizontally. For this particular period, they have a skin depth, so they see the top. They also see a little bit deeper, of roughly a couple hundred kilometers. So they see mostly the plates, mostly the lithosphere. Right? You know what a surface wave is, right? Okay. That's a short arc, so that's the minor arc Rayleigh wave. And you can tell that's the minor arc because you have coverage in the upper hemisphere. If you have the major arc, you will actually get lower hemisphere coverage. So for tomography, it's important to actually use the major arc data as well. So the long way around the Earth, because that's the way to actually see the southern hemisphere. Yeah. Thanks for asking. It's good.
In S-ray, there's a single line where it says Euler.
Oh, this is a lot more complicated than I had envisioned, this whole tutorial.
And then you go to Euler. Well, it shouldn't be open, actually. Oh, and you already changed it to 2. So try running again the inverse tutorial code. Okay? So you have to make sure you're in the same direction.
You guys have a map? You have a problem.
If I run it, I put 5.
Where's your inverse tutorial? Where did you put it?
4.08.
It's right there.
What?
Okay, and now open up the inverse tutorial.m.
I fixed his suggestion.
Oh, you got to talk
So
to.
if I do this enough, something happens.
Oh, Vet, can you help out with?
Yeah. It's the Flintmax Bitmax thing, yeah. That's okay.
So I think we should all program in C.
But it doesn't give you an error message.
It solves a
anymore?
lot of problems.
You have
It
some kind of weird computer.
No. I have probably a more recent version of MATLAB than most people.
You guys have a map?
I'm running 2015, I think.
Are you bored now? You want to go on?
I can close my MATLAB.
Oh, cool. Look at that. Yeah, that's great.
Maybe.
So that's typical hit count.
Well, is it supposed to, like, when the first time I ran it, ran
What-
a bunch of...
Looks like a sickle. Looks like a Russian
And once
sickle,
it
right?
figures it out and you're redoing the same thing, it won't
Oh,
recalculate
the
them
little-
because
the
it
little
wants to
thingy
be
there.
smart.
Okay, good.
It's the Western Pacific is ruled by the.
Yeah. Why? It's not an anomaly. So this, have you explained to them what this map is?
Yeah.
Okay.
I can do it again.
Yeah, please do.
So this map. So what is the map again? I'll go over it again. The map shows you hit count. It shows you where the waves have gone.
No, that's not.
Right. So it's basically every block. Basically, for every block, you count how many waves have gone through that particular block.
Yeah, it's so stupid.
Okay. So here are your 5 by 5 degree blocks. You can see the little squares. Those are the 5 by 5 degree blocks that we've chosen to use. And in the blue area, so for example, right here in Nigeria, I think it is. Well, it's actually the Atlantic Ocean, but 0, that we use a cross section. There are only about maybe 200 or 300 waves going through that particular block. Whereas if you look at Japan or northern Japan, there are thousands of waves going through that particular block. And this is very typical for these types of data because you have most earthquakes occur in the Western Pacific. Most seismic stations are in the northern hemisphere, right? And if you're looking at the short arc, the short distance between earthquakes and receivers, you will basically propagate primarily in the northern hemisphere, not in the southern hemisphere. Okay, but this bias, this variation in hit count, this is what's going to determine primarily variations in resolution. Okay, if you're going to look at tomographic maps, so you can do these checkerboard tests that we'll do in a minute, you'll see you can predict that the checkerboards will be recovered very well in the northern hemisphere and not so well in the southern hemisphere because the hit count is just different. You also see very nicely that the hit count really has a sharp boundary within the Pacific itself. Okay, this boundary is essentially because you have earthquakes in the Tonga, Fiji. We have lots of stations in North America. We have fewer stations in Central or South America. So you're seeing here this boundary right there is essentially telling you that all the stations are in North America, but not in Central or South America. Okay. Shall we move on to block 2? Yeah. Let's go. Yeah. I know.
Yeah. So who has not produced that map, even if it's ugly? Sorry. Sometimes it looks weird and distorted for some reason. You haven't? Why? It's old? Oh, slow. Okay. Someone back there also didn't. Oh, I see all the computational people don't know how to. Your chemists are awesome. It means we did it right.
Okay, I'm going to click on block 2 and do Command Enter. So what we're going to do is we're going to do an inversion of the data, and we're going to make a model. And it's going to ask us how we want to, what do we want to do? Because we have to regularize the inversion. If we just do the inversion directly, we will get rubbish. We have to add a priori constraints because it's an underdetermined problem. We have not enough data to fully recover the wave speed variations on the Earth's surface for this particular wave. Okay, so I'm going to make a choice, and I would suggest that you follow me. I'm going to type here 0.1, and that basically means that a priori we're going to look for a model where I'm going to assume that the variations in wave speeds is 0.1. Okay, so that's called a damping factor. I'm going to push the model towards a solution where the variation in the model in the model strength is at most 0.1. Okay. The smoothing, I'm going to turn that off for now. So we're not going to apply any regularization in terms of smoothness. So I'm going to set that number to be 0. So we're only going to apply norm damping. We're only going to apply a damping to the inversion, meaning that we're going to tell the inversion, look for any model that you like. It might be rough, it doesn't matter, but make it as small as you can. Make the variations from the reference state, from the reference velocity that we set, 4.08, make those variations as little as possible. Add variations to fit the data, but if you don't have to do anything, if there's no data, constraining a particular region, set the model to be the reference model. That's called norm damping. So for now we don't do smoothness, so we set that to be 0. Okay? And so it's going to calculate some covariance matrices. Oh shit. So fucking tired of MATLAB. I'm not a MATLAB guy. Please. Yeah, I know, I made a mistake. It's my mistake. So I'm going to make this 0.1. Okay. Okay, so there you go. So there's my model. Okay, so we made a tomographic map of wave speeds of 100-second period Rayleigh waves propagating along the Earth's surface. And we made that by imposing the constraints. We made it using, first of all, blocks of 5 by 5 degrees, right? So that's your implicit regularization, as Red calls it. And then secondly, we had an explicit regularization, is that we applied some norm damping. We said to the inversion, don't worry about smoothness, make it rough if you like, but keep the velocity variations within 0.1, or try to keep them within 0.1 kilometers per second. You didn't get the plot? So you may have to click on... click on block 3.
Yeah.
You may have to click on block 3 and then do Command Enter to get the picture.
Jeroen merged his block 2 and 3.
Yeah,
so first you run block 2, it does the calculation, and then you run block 3, and it does the plotting.
Okay.
Did that work?
Did it work?
I'm so sorry. Oh, that one worked. Not really. Oh.
So what do we see here? Geologically or geophysically, what do we see? See the ridges? Yeah. You see the continents, right? So these waves are sensitive to 100-second Rayleigh wave is sensitive to the top 200 kilometers or so of the Earth surface. Most of the sensitivity is at the top, but there is sensitivity all the way down to about 200-300 kilometers. And so you see, therefore, that's your sensitivity. You see, therefore, the top 200 or 300 kilometers of the Earth, right? You don't see LSVPs with these data. If you want to use if you want to look for LSVPs, don't use Rayleigh waves. You have to use a different data type, of course. You see what? The Japan high velocity anomaly. All right. Yeah, that's probably the oldest. That's probably the oldest ocean. So you probably see a little bit of ocean thickening. The what do you call it? The age of the ocean as the lithosphere gets older, gets colder. So you typically see that in the wave speed structure as well. So you see the ridges, and then you see the thickening of the lithosphere with increasing ocean age or plate age. Right? Shall we try a different smoothness? So if we're going to reduce that, if we were going to, let me go back to my editor. Click on block 2 again, and then do again command return. Okay, and it should ask you the same questions. Instead of 0.1, let's try 0.01. Okay, that means that we're going to look for variations in wave speed that are going to be very small. We're going to prefer now models where the wave speed variations from the reference model are much smaller, right? Only 0.01. Okay, that means that you're really pushing the model to be close to the reference structure, right? So if you do that, so let's try that 0.01. That means that you increase the damping considerably. You're really damping the model to the reference structure. Again, use a smoothness of 0 for now, so that we don't smooth the model. Smooth the model. Notice that the chi-square, I'm not sure if you pay attention there, but the chi-square here is 7. The chi-square is 7. In my previous inversion, the chi-square was, I think it was about 1. Yeah, so the chi-square has gone up considerably. That means that your data fit is really worse. You're not fitting the data because you're telling the inversion, I don't care about fitting the data for now. I just don't want you to move away from our reference structure. Right? We really want to be close to what we started with, which is the reference velocity structure. And you see here now too that look at this map, and we can probably compare it to the previous one. Where's figure 1? Oh, do you overwrite those? Well, I think you overwrite the figure. I thought we kept the old figures too. But what you see now is that you no longer see clearly the ridges. and you no longer see clearly the content structure. You really, and also look at the velocity variation. We used to have velocity perturbations of about 4% before in the previous map. Now we only have velocity perturbations of 0.5%, right? Very small. So we have a poor data fit, we have very small velocity variations, and we have only velocity perturbations in very few places. Okay, that's damping. That's just the effect of damping. So the only places where you do get some structure is places where it really makes sense to add some perturbations because it really helps fitting the data. That is really worthwhile doing. But for the most part, the inversion is perfectly happy doing nothing because you impose such a strong damping. You impose such a strong constraint on, well, you impose so much to the inversion to stay close to the reference structure. Dan, you had a question? What's that? Only the strongest velocity variations survive. Those make sense. Those make sense, but for the most part, the inversion doesn't want to do anything. You're damping it almost to the reference structure. Right? I wish you had the previous map too, but I don't know why.
You can see that the areas where you do have structure are the areas where you had a lot of data.
Yeah.
So it's like your data is like polluting what you get, because the only place where it's going to put anything is where a lot of data really asks for it. But the problem is that we have, our density of data coverage isn't necessarily related to where we have interesting structures we're interested in. So you have to be careful when you damp.
I'll do one more just to, for the sake of. So I'm running an inversion myself again with now a lower damping, just to see the contrast again. Chi-square is 1.3, right? And here's your map. Oh, now the old map is back. So now we can compare the two maps. Low damping on the left, or high damping on the left, low damping on the right, right? So you see small variations in wave speed, and where you have variations in wave speed, only in the places where you have a lot of data. Here it makes sense to make changes. But for the most part, nothing changes. Whereas here, this is a relatively low damping model. So here you allow the inversion to be more, to move away from the reference structure. And so if there is sufficient data to tell you there must be a variation, there must be deviations from the reference structure, it will put those in, right? And you see also that the variations themselves are much higher because you damp less. Okay? Yeah, Steve.
Interesting feature. Offshore Japan, the high damping actually had higher amplitude anomaly than with low damping.
It's not. It's the color bar has changed, sadly.
Yeah, the scale's different. Yeah.
Sadly. Otherwise, you wouldn't see anything, I guess. Yeah.
Yeah, this effect across the ocean basin, basically from low to high, the fact that you have, higher wave speeds below or in the plates that are the oldest, that's a very robust feature that the data really want you to the data really want that, so it's in the models. Okay. Yeah, look again, and look also at the chi-square, right? So this is the data fit, right? This tells you there's a number of data fit. You like that number to be 1. That tells you that you have a good balance between fitting the data and the errors in the data. That's basically what chi-square tells you. If your chi-square is very high, it means that your data fit is poor compared to the errors in the data. There's really structure in the data that is not represented by the model. So there is actually, you're underfitting the model. You're underfitting the data, I'm sorry. The model is underfitting the data. But the reason is that you impose a model to stay close to the reference structure. You don't like those variations to be there. Okay, so let's run it again and let's add some smoothing to it. So I'm going back to this block 2 of mine. Click on it and do command return. And what did I choose? Yeah, I'm going to choose 0.1. So we have a norm damping. We tell the model to stay within 0.1 kilometers per second as much as possible. So preferably the models stay within a variation of 0.1 kilometers per second. And then we're going to also add a smoothing length scale to the inversion. So in the tutorial, there's this formula for the covariance matrix, where you're applying essentially a smoothness by applying a included is an exponential function where you implicitly say that you are penalizing models where you have parameters or model parameters that are over length, or if your velocity variations are vary over a particular length scale. Okay. So let me just put in a number here. What did I do? Let me try 2. So if I put here 2 degrees, that means that I'm telling that block size over 2 is 2. So I'm telling basically that the smoothing length scale is 2.5 degrees, roughly. Is that right?
No, I think it's 2 degrees. So the try block size over 2 was just like what you should try, or you might want to try.
That's right.
But it should be just literally in
Yeah,
degrees.
2 degrees.
So variations smaller than 2 degrees won't matter. But the boxes themselves are bigger than 2 degrees.
Right? 5 degrees, yeah. So I probably should use a bigger number now.
If you do 10 degrees, then it's like averaging over 2 boxes.
Yeah, let's do that. So I'm going to do 10 degrees.
But it always has an effect, so it's a little tricky. Yeah.
But you'll see the effect here in a minute. So what we now also tell is that you are trying to keep variations. You're penalizing variations over too short length scales. So you're actually adding some smoothness to the inversion. Okay.
It looks now. Okay.
Right. So you'll see it visually, right? What happens? So we have the same norm damping, 0.2. Oh, that's 0.1. I'm sorry, but it should be about the same. But then the smoothness of 10 degrees. So it's basically a 10 degree. Think of it as a 10 degree spherical block, spherical cap. That's basically averaging the wave speed variations. That's not quite like it, but think of it that way. You're smoothing. You're averaging more across the Earth. So you get a much smoother model. Right? Which one is better? Which model is better? Chi-square wise, well, I would say they're almost pretty much the same. 1.3, 1.5, right? So that you fit the data equally well. So you have two visually different models that fit the data well, fit the data equally well. You can either have a nice smooth structure, or you can have blocky structure, right? So when you're trying to interpret these two models, you might think here like a whole ridge that's all screwed up by whatever. You have all these little blocks of high low temperature variations. Well, a smooth model will do equally well. Right? So this is again very typical. We're making a choice. We're either making a choice of a smooth model or a model that looks rougher. And it's just which one you like better. It's just actually just visual. They fit the data equally well. Look at this structure here. Look at the structure here in Nigeria again. This is the Western African craton. It's pretty pronounced here. It doesn't really pop out so well here.
I guess the way you can understand that is if you have structures that show up in one map but not in the other map, sometimes if there's not that much data there,
Sure.
then the norm damping will erase the structure, whereas the smoothing will just make it look longer wavelength.
Yeah. Sure.
I mean, both are wrong, but in different ways.
Okay. So block 4 is a checkerboard test. Okay, so let's do a checkerboard test. So now we're basically saying, well, what is the recovery of a certain pattern by the data? So in fact, if the Earth is a checkerboard, which it isn't, but if it is, it's actually a really silly test because you're testing whether the Earth is a checkerboard, which is, I know, but we know it's not. But what if the Earth is a checkerboard? What would you see? Okay, what would you see? So, well, let's find out. So it asks us what sort of checkerboards we want to look at. What sort of wavelength of checkers do we want to look at? And that's expressed as a spherical harmonic. So I suggest that we try 8, spherical harmonic 8, which is, sine 8x over the Earth's surface, right? So it's a very small, very long wavelength structure. And so there it is. That's our degree 8 checkerboard. And if this was the real Earth, then we would recover the thing in the bottom, the checkerboard in the bottom, right?
Quick note, on yours, that error map is going to appear below the other two resolution tests. There's nothing wrong. That's the correct behavior. It's just the top two are the resolution test, and the last one is the error map. Yeah. So in some sense, it would be like plotting the diagonal of the posterior model covariance matrix.
Right. You got that?
Is literally the uncertainty on your model parameters, and because your model parameters are just 5 by 5 degree boxes, then the model uncertainty on that parameter tells you what the error is on the velocity in that box. So the blue means less error, and remember, it kind of mirrors that data distribution map, because data kind of controls the whole thing.
Hang on, my wife's calling. Hello? Hey, Shanti. Okay. Can you hide the key somewhere? The whole audience can listen in on our conversation, by the way, but oh, it's also recorded, by the way, so this will be it's streaming it worldwide now. So tell me where you hide the key. Yeah, keep it unlocked. Everybody can come. There's beer in the fridge. How many beers? About only 2. All right. Okay, no beer for Jean-Paul. Okay, fine. All right, bye. All right, so yeah. So your resolution, so degree 8. So what do you see? Is it good? Is it bad?
You mean you have like red and blue opposite? Oh, that's okay. Okay. Oh, beautiful.
So is resolution good or not? I mean, what can you learn from this particular? If the Earth is a checkerboard pattern, had a checkerboard pattern, this is what you get. But you can see the amplitudes are a little bit lower. You can't see it too clearly, but the amplitudes are lower. Well, that's what we impose. We told the inversion, keep the variations in wave speed up to 0.1 ideally, and smooth things out. So average the velocity variations a bit. Right? But overall, the pattern is reasonably well recovered. That tells you that, well, you have to be very careful with these sort of tests, but it tells you that a degree 8 type variations are can be reasonably well recovered given the data that we have for this particular Rayleigh wave. Okay, so let's try to be optimistic and make this pattern a little bit shorter wavelength. Okay. So we run this again, and I'm going to make this now degree 12. here's degree 12. So shorter wavelength structures, still pretty good. But you may see something already that we saw in the hit count map as well. You're seeing already starting that the variations, that the recovery of the checkerboards is a little bit better in the northern hemisphere than in the southern hemisphere. At least I can see it from where I'm standing. But right? I'm going to run it one more time, and I'm going to try. I'm going to try now degree 20. And so now you see that the whole thing falls apart. Right? There's a few checkers in the central Pacific, in the Western Pacific. That is not too bad, perhaps, but overall, you just do not recover at all the pattern, right?
If your maps look insane, as in like, they're all white, and then maybe there's like 3 kind of red, white, red, and then the error map just looks green and maybe has a couple of things, that might indicate that the prior model matrix that you put in had, for example, a long correlation length, and when the computer tried to invert it, that kind of a matrix actually has a very bad condition number, so it's a very unstable thing to invert. And so usually you can fix that by making your correlation length a little bit smaller, and then the inverse will be better behaved, and you'll have maps that look less like numerical errors.
That's good. I'm going to try 16. I want to see if it's sort of. I want to see that pattern.
Oh yeah, perfect.
Yeah. I want to see the nice sort of, you see now the northern hemisphere versus southern hemisphere variation. So this is very clearly, where you're seeing, the effect of data coverage. Data coverage is pretty good in the northern hemisphere. You somewhat get the pattern. It's not ideal, not perfect, but much better than the southern hemisphere. Right? Hey, Ved, do you want to do the SVD too, or you want to? It's a bit.
So why don't we have a show of hands? There's 2 other additional blocks within this tutorial. Depending on whether or not you want to play around with this more, or you're completely lost and not getting anything out of it, or you need more help, we can just leave those 2 for you to do when you're really feeling that urge and itch to do some tomography. Otherwise, we can just, because there's 10 minutes left, we can just...
we could start from the beginning and do it one more time, if that's useful. I think it is, but...
Who would like that?
Who doesn't care? I take that as everybody. Steve. See?
Oh, they give you a suggestion.
You want to do the next 2 blocks? Okay. All right. It's SVD.
Yeah. Mapping the model null space. Kind of.
Yeah, I like the SVD myself, but let's do it then. Okay. Yeah.
I just point out some of these things have produced very large output files that have cluttered up my hard drive.
Sorry, man.
No, so just to point out.
Yeah, at some point.
Replace them as it brings new on each with different parameters. So I've just been deleting the old one.
Yeah, there's a block 8 where I think you clean up the disk, right? So there's a final block that you can, but do you have to run it after you're completely done, or?
It saves those things so it doesn't have to recompute them, but you can feel free to kill them and then it'll just compute them every time. And by kill them, I mean delete them. Also, you should get a bigger computer.
Okay, so I'm going to do the last. I'm going to do an SVD inversion. And so you haven't really, Fred, you haven't really covered SVD very much, right? So the way I think of an SVD inversion is that you are essentially just choosing the number of model parameters that you want to invert for. So think of a tomographic model as a sum of, so it's a model based, so we have how many parameters? I'm not sure how many parameters we have. We have something like 1600 model parameters, right? And so not each. So think of a model as a sum of think of a model as a sum of models, of 1600 models. So that sum would represent then the tomographic model. Or think of it as a if you think of an eigenvalue problem, if you have a matrix that you can decompose in eigenvectors and eigenvalues, you can think of a model as a sum of eigenvectors of model space, right? Each with a weight, an eigenvalue that determines how much of that particular model vector is contributing to the final model. So with an SVD inversion, you can simply just truncate. You can choose a model based on the size of your eigenvectors and eigenvalues. Okay, so let me just run one, and you'll see what's going to happen. What I mean by all of this. So what we're going to set is a threshold. We can think of a model as a sum of eigenvectors and weighted by the eigenvalues. Okay, the largest eigenvalue would be 1. That's how the model is normalized, or how the eigenvalues are normalized. And we can say, well, choose that model until you reached model vectors that are contributing to the models which have an eigenvalue lower than a particular threshold. Okay, so if I choose here, let's just choose here 0.05, for example. It's going to find now the eigenvalues and eigenvectors of the model, and it's going to sum up all the eigenvectors for which the eigenvalues are at least 0.05 of the maximum eigenvalue, right? So it's going to sum up all the models that have a more than a 5% significance to the final model. That's how I sort of look at the whole thing. This is a little bit of, this might actually take some time. How long does this take, Vet, for a 5 by 5 degree? That takes a bit of time, right, to get the SVD?
Oh yeah, the SVDs will take a while.
Oh, crap.
Oh really?
Yours is done?
It read a saved SVD.
So how long did it take to run that one?
Oh, you read a saved one.
So what it'll do, once you run it once, it'll save them, and then it'll be super fast next time.
But this was a saved one, so this is not necessarily 5 by 5.
There's probably some warnings in the PDF not to do it on 5 by 5 or something. It'll finish.
It'll do it.
But you can see that this is a computationally heavier approach, and therefore it's one that people use less often.
So I use it on a 32,000 by 32,000 matrix vet. Takes 9 days. Yeah. But then you have the whole thing. You have the whole decomposition. Yeah. Is yours done? Yeah, I have a crappy computer, man. It's like 6 years old.
Has anyone's finished? Oh, good.
Well, I need a new Mac.
You and Jonathan can go shopping together.
And does it plot it automatically? Okay.
Block 5 will do the plotting.
Yeah. So if you have it, then you just plot it and look at it. And then the next exercise will be to actually increase this number. So you might make this 0.2. if you're ready for that. And you should see that your model should be different because you are cutting off the eigenvector sum or the decomposition earlier. Wow. You're still working too? Is yours done? Yeah, try something with a different SVD number. So make it 0.2. Oh, the plotting is a different the block next to it, block 6. Yeah, I combine the blocks. Plotting? You know which SVD routine I use? It's written by Gilbert in 1969 or something like that. And it's faster because it's faster than any other routine that I've tried. Yeah. It's incredible. And if you look at the code, it's unreadable. It's like this block, Fortran block without any indentation. Just. My computer's really slow.
Might be memory buffering.
Yeah, I don't know. It's just. That's why I did 10 by 10 all the time. So if you have it already, you may want to just try it again and then make this number 0.2 and tell me what you see. Smoother, right? Simpler, smoother. Why? Yeah. So the SVD decomposition, the smaller the eigenvalues, the less those really contribute to data fitting. Think of it that way, right? The higher eigenvalue, the eigenvectors of the model, or those components of the model with the associated with the eigenvalues, those are the ones that actually are fitting the data. The ones that have a lower eigenvalue are less important. They fit the data. They don't add much to the data misfit. Right? So the fewer you keep those extra components, the simpler your model will be, because those are the ones that matter to fitting the data. So it's a similar way of regularization. Smoothing or damping, you simply can just cut off the eigenvalue decomposition, just choosing those components of the model that matter to the data fit. And those are usually, because of a tomographic model, because your data are essentially integral, they provide integral constraints. You're measuring average wave speeds. The biggest components of the model are usually the long wavelength components, because those matter to the travel times. Which one has more artifacts?
Yeah, you can see like ray pads essentially and various other data coverage artifacts in an SVD inversion if you drop too many, because the patterns that you're kind of adding in the SVD, those patterns reflect the data sensitivity.
Yeah.
So
they're not necessarily, they're artifacts, but they're also not, right? I mean, it tells you that there is data from one point to the other that really wants a high velocity path. And so if you would actually do a resolution test on that particular structure, you might actually find elongation along that path. It is an artifact. It's probably not real, but the data really wants that path to be fast. And so if you include that. Okay, my computer is really slow. If you try that number to be, instead of 0.2, try 0.5, and it should get smaller still, right? Etc. What is the second block? That's the other block. Was there another block on this after SVD? Because it's 3:30, but I think it's okay now.
Yeah. Well, it's 3:30, so as usual, time has interfered with seismology. But it looks like most of you got things to work. I apologize for some of the plotting issues. Yeah, block 7 was to plot the thing, and then you can do some resolution matrix tests with the SVD. And then block 8, if you kind of want to, oh no, yeah, cleanup doesn't remove those files. But the SVD files and some of the other ATA files or GTG files or whatever they're called, they can be quite large, like 500 megabytes, as Jonathan pointed out. So if you want, feel free to delete them. All that'll require to replace them is to rerun the code once. So it's not a big deal. And thank you all for trying. Yeah, they're going to be saved in whatever directory you ran your MATLAB. And if you ran it successfully, it should have been the directory with the inverse tutorial. So they're all going to stay there. They won't pollute around your computer, just in that one place.